Today we're delighted that our speaker is Professor Gyuboong, currently the Harilela Associate Professor in the Department of Physics. Professor Zhou received his PhD from MIT in 2010, I believe. And following a postdoc at UC Berkeley, he joined the faculty of HKUST. Professor Zhou's research explores the interface between atomic physics, condensed matter physics, and quantum information science using quantum simulators and ultra-cold atoms. Professor Zhou has received many awards since his joining the faculty here, including the RGC Early Career Award, the Croucher Innovation Award, the UST School of Science Research Award, and most recently, the RGC Research Fellowship. Today, Professor Zhou will discuss the 2022 Nobel Prize in Physics awarded to LNS Pan, John Clauser, and Anton Zeilinger for their experimental work in the foundations of quantum mechanics. So please join me in giving a warm welcome to Professor Zhou.
Thanks, Andy, for giving very general introductions. So good afternoon, everyone. Thanks for coming to this popular science lecture at IAS at HKUST. My name is Gyuboong from Department of Physics. And today, I'd like to introduce how these three gentlemen contribute to understand one of the paradox in quantum mechanics that was pointed by the Einsteins almost 100 years ago. And I would like to convince all of you after this lecture that this quantum mechanics really works and our nature behave as we expected in the quantum mechanical way. So Einstein actually thought about very peculiar situation that what if we bring two particles, usually quantum particles, and let them interact a little bit and move those two objects very far in the opposite directions. And he actually considered this situation as the spooky action at a distance. Okay? So what I mean by here will be very clear in a minute. And to answer or to resolve the paradox, these questions, those three gentlemen basically did a lot of experiments to support the quantum mechanical interpretation of the nature, including the LNS Pan from France, and John Clauser from the United States, and the Anton Zeilinger from Austria. So their significant contribution to this paradox, or the foundation of quantum mechanics, is all about their experiments that explore the entangled photons, and they establish the violation of the Bell's inequality, which lays the foundation for the quantum information science. So here I just highlight a few words, which is the key words of this the work. First is entangled or entanglements. Second is the Bell inequality, and those concepts actually put a lot of the information for this quantum information science, which is the hot in these days. So before we get into the more details, let me first set up the problems, what Einstein got in. So here, let's think about two objects. One in the white, and the other one is the black. And this is a very classical situation. So let's first assume that I have a two object or two balls with different colors. So this is my pre-assumption. Then I just let them interact at the beginning and put apart at a long distance. And at some points on the right-hand side, I just observe the color. You take a look and just check the color of the ball. And nothing is special in this situation because once you know that the ball on your right-hand side is black, you immediately know the color of the other balls. So this is very natural in our life because the color of the ball already exists. Okay? So in our life, not everything already exists. For example, the white ball is always white. The black ball is always black. But in the quantum mechanical world, this is not always true. And what makes the quantum mechanics very special is as follows. So in a quantum mechanical way, you can say that the ball, the color of the ball is not just white or black. It can be understood as the gray color. The gray color can be interpreted as the mixture of the white and black with a certain probability. And here, let's think about more sophisticated Gyuboong experiment or thought experiments. So in the middle, we have a quantum box or quantum machine that actually contains the two balls. And they somehow interact. And at a certain point in step 2, it suddenly sends one ball to the left, the other ball to the right. In a quantum mechanical way, we say that the color does not exist until the observer on your left or right, we call it Alice or Bob, until they really look at the color of the ball, the color does not exist. In some sense, we call it just gray color because we don't know the color, either white or black. It only determines the color when observer, either Alice or Bob, look at the ball. So this is the quantum mechanical behavior, and Einstein and many other colleagues actually got in trouble because especially when we say those two balls exist in the shared quantum states, which is called the entangled quantum states that we'll actually explain in a minute. And what if the distance between these two observers are very far, at a long distance? This interpretation does not make sense, in some sense, to the Einstein and his colleagues. That's why they propose some paradox and try to understand what's going on. So in the coming slides, we'll try to understand how they build up this paradox and how those three gentlemen actually prove that the quantum mechanical way always correct in nature. So to look at this problem, we need to step back a bit and think about the most fundamental quantum objects, which is basically atoms. So historically, this quantum mechanics was developed to understand many different things, but one of them is atomic structures. So here I put one of the revolutionary steps to understand the internal structure of the atoms. And this gentleman, the Bohr, he actually proposed that this internal structure of the atoms should be discretized with some quantized orbits. And the electrons, which is the very important component of the atoms, just move around this nucleus at the particular orbit, which is set by this quantum mechanical orbits. And he could actually explain many interesting experimental observation based on his atomic model. But unfortunately, his model is still not complete to understand the internal structure of the atoms, because in the quantum mechanics, you cannot simply say that the electrons in these atoms exist somewhere at a certain moment. All you can say that is we only know the probability that electrons exist somewhere within a certain volume. And in the Schrödinger's atom, he already pointed out this probability picture. And according to this probability interpretation, the real atomic structure looks like this cloud because it represents how likely you find the electrons in a certain orbit. And the orbit is not that sharp, and it has some finite width with certain probability. And this is a very important concept in the quantum mechanics, that everything in the quantum mechanics should be written, described based on these probability interpretations. So when the people, actually physicists, try to understand this probability and the quantization in quantum mechanics, they actually evaluate this kind of Gyuboong experiments. So here, let's think about this Gyuboong experiment again. So we have a quantum machine with two balls inside, and we send one ball to the left, the other ball to the right. So where is our quantum system? Well, our quantum system is basically there. Inside the quantum machine, I have two balls, which consists of my quantum system. So before, I mentioned that the color of the ball might be gray, which is written in this way, because based on the Schrödinger's pictures, the quantum mechanics tells us about the probability of the states we actually see. So the gray ball can be understood as the superposition of the white ball and the black ball with certain probability. Here I put the number W and B in this way, and the probability that you find the white ball should be W squared. On the other hand, you'll find the black ball with the probability of the B squared. If you ask why the probability is not just B or W, it's just because of some mathematical normalizations to make the probability make sense. So in this picture, actually we have these quantum states, which I describe as the gray ball as the superposition of this white and the black ball. So this is our quantum description of this state or system. And if you are familiar with the very hot technology like quantum computing or quantum information science in these days, this superposition principle is one of the building blocks for these technologies. For instance, in these three-dimensional spherical representations, this black and white ball, they are corresponding to the North Pole and the South Pole in this spherical representation. In between, there are infinite number of points that contains so-called quantum information in this case. And we call it qubits, and this qubits contains a lot more information than the classical information units, which is called the bits. But if you look at this Gedanken experiments, the thought experiments, there is another very important process, which is called the measurements. Because when the ball travels from this quantum machine to the Alice or Bob, those two guys actually take a look, the color of the ball, and this process is basically called the measurement. And this measurement is more than just measurements in the quantum mechanics, and it actually perturbs the quantum states. And for example, many physicists, including this Paul Dirac, realize that whenever you measure something, these quantum states jump into the right states, which we call it eigenstates in this quantum language. And this measurement process actually projects your quantum state to the other final answer or final observations. So in this superposition quantum states, for Bob on your right-hand side, he sees the black ball just because this gray ball or this superposition states travel to the Bob, and he just measure, and he end up having this black color. So he sees this black color ball through these measurements. So this is quite important step in the quantum mechanics, but this measurement has some limitation. You cannot measure everything simultaneously in a perfect way because of this very famous uncertainty principle in the quantum mechanics. So whenever you do some measurements, you need to remember that for a pair of the quantities with some special relations, you cannot determine those two quantities simultaneously in a perfect manner. One example is the position or momentum. So if you have the ball in our Newtonian mechanics, if you throw the ball, you know the position of the ball and the speed of the ball in a perfect manner. But in the quantum mechanical way, you cannot determine both simultaneously. For instance, if you know the position perfectly, you have to sacrifice the certainty of the speed or the momentum of the ball, which is what the uncertainty principle says. You can choose different quantities, which we will actually will be interested in soon. For example, some particle in the quantum world has the intrinsic angular momentum. So basically, the ball we are talking about here just rotates by itself with certain angular momentum. And you can actually observe such kind of angular momentum along the different axes, like along the x direction and y direction. And you can determine this angular momentum along these two different directions. And according to this uncertainty principle, you cannot determine both simultaneously. Okay? So this is quite important, so please remember this uncertainty principle, because in the Einstein's paradox, we need this important concept. All right, so far we discussed superposition states in the quantum mechanics, measurements in this very simple thought experiment. However, in the history of the quantum mechanics, those kind of concept was kind of well founded and established through the several conferences and meetings in the old days. For example, in this first Solvay conference, people, the physicists, they set up and they agree with each other about this foundation of the quantum mechanics. But at certain points, for instance, in the third conference at Solvay, they realized some challenge in the quantum mechanics. I mean, this is how this Einstein and his colleagues started to realize that quantum mechanics might have some problem, although the nature seems to behave following the quantum mechanical principle. So why was the Einstein confused? So we look at the same Gedanken experiment. Still, I have a quantum machine with the two balls inside. And after some preparation, we send one ball and the other ball in the opposite directions. But we could imagine slightly different explanation, not following the quantum mechanics. That's why I put the hidden variable picture, which is not the quantum mechanical interpretation. And Einstein actually feels that this makes sense more than quantum mechanics, because if you look at the ball in your life, every ball has the color, basically, which means the color is real. Okay? So color is real in a local frame. So what he believes is, in this quantum machine, the color of the ball probably just doesn't show the color to the observer yet. But whenever it travels to the Alice or Bob, it suddenly shows its color to the observer because of the hidden or secret information encoded inside the ball. So this is so-called the hidden variable picture. What it means is every system has the hidden or secret information depending on where you are. So it actually solves many uncomfortable conditions, because whenever the ball travels to the Bob or Alice, whenever the Bob see the ball or take a look at the ball, color just naturally shows up, because behind the ball there is a hidden or is already determined information. So this so-called hidden variable picture can explain this Gedanken experiments without the quantum mechanics. But obviously, our standard quantum mechanics says ball should be gray color with the superposition of the white and black color until Alice or Bob take a look at the color. So in this situation, both hidden variable and quantum mechanics, they can both explain this situation pretty well. And until the John Bell in 1960s looked at the problem again, this kind of questions was regarded as the philosophical questions. Most of physicists just chat about these possibilities during the coffee break or lunch break, because it's simply philosophical. It was not that much physics at that point. Just because there was no experiment to check which scenario is correct. And unfortunately or fortunately, all the observation in nature seems to follow the quantum mechanics in these days. And physicists believe, okay, quantum mechanics must be fine, but they don't know how to disprove these hidden variable pictures. But obviously, the John Bell, he actually devised a very clever mathematical way to differentiate these two pictures. And those three gentlemen we introduced today, they actually confirm his framework using very sophisticated sophisticated experiments with atoms and other devices. So let's look at just one more concept to understand what or how this John developed his inequality. So one more concept we need to learn about is the entanglements. So in the beginning of my talk, I told you that the quantum mechanics seems very peculiar when the objects exist in a shared quantum states. More precisely, this sharing should be considered as this entanglement, but this is so common in nature. So in the previous slides, we looked at how we describe the atoms based on this Bohr model or Schrödinger's atomic model. But we can imagine the second simplest atoms, which is the helium atoms, in these slides. And almost 100 years ago, people already calculate how this energy spectrum looked like for these helium atoms. And these helium atoms has the 2 electrons in the certain orbits. And people already realize that instead of the 1 electrons, if you have a 2 electrons, which look like our white and black ball, the situation is a little bit more complicated. And we need to think about how those 2 electrons or 2 balls exist in the shared quantum states. And actually, the Schrödinger point out that this is called entanglement. He actually wrote this paper not about this helium. He just wrote this statement after he saw this Einstein's complaint or Einstein's concern about this quantum mechanics. But this is deeply connected. Even before Einstein realized this entanglement effect was there. For example, in the calculation of the helium atoms. And if you look at our states, our quantum states for the helium atoms, you can imagine that these 2 electrons is exactly the same as our white and the black ball. But instead of the color, I probably use this up arrow or down arrows because each electron has its own angular momentum. It just spins by itself. So I would say it has a spin up or spin down, or either up arrow or down arrow, and so on and so forth. And our states can be written in this way. This is a very mathematical formula, but you might be confused. But this is a very natural way to write down the quantum states. Just because there are only 2 possibilities that those 2 electrons or 2 balls share the quantum states. One possibility is you find the white ball on your left, and automatically the black ball should be there. So that's the first term in these states. And the probability should be proportional to the square of the coefficient, which means half. So with a 50% probability, you will find the first configuration. The other configuration is you might find a black ball on your left-hand side and white ball on your right-hand side. That's why I put the second term in that way. It's still the same as our previous superposition states, but I just put more details in terms of the configurations. And whenever you write the quantum states in this way, we call it entanglement or entangled quantum states, because these 2 objects, white and black ball, even though they are very far, they share the quantum states, or they exist in the shared quantum states. You might be wondering why I call it very far, because the electron is so small. And for the electron's point of view, it's very far. Okay? So that's a situation we are considering right now. And now the Einstein start to ask himself, what if we have a very remote entangled pair? Simply saying, I have a black ball and white ball from the quantum machine. So here we put the S indicate the source of these 2 objects. So we generate this entangled pair, or 2 balls, 2 quantum balls out of this quantum machine. And Alice and Bob, they're very far with each other, and they just measure the color of the ball. In the real experiments, it can be color or it can be some other parameters, for example, the direction of the angular momentum, but always we measure something at the Alice and Bob's positions. And again, our quantum entangled states or shared states, it can be written in this way. So instead of the black and white ball, I use this up arrow and down arrow, or down arrow and up arrow, because there are only two possibilities that Alice and Bob can measure in these configurations. And you can imagine this way. So whenever the Alice measures the spin up or up arrow at her positions, so the Bob states instantly determined by these measurements. And vice versa. If the Alice measures the spin down, which is corresponding to the second term of these shared quantum states, Bob's states is automatically determined by the spin up or up arrow, which is a little bit unreasonable to the Einstein, because as long as the Alice and Bob is very far, like Earth and the Moon, how come this information can be transmitted from Alice to the Bob immediately? Quantum mechanics says whenever I do the measurements on the Alice side, I immediately determine the states of the Bob immediately, which is contradictory to the maybe cause and effects or relativity in Einstein's point of view. And that's the reason why Einstein proposed that there might be spooky action between these two guys, between Alice and Bob. And he actually tried to write some papers about this paradox. And related questions also raised by the Schrödinger's, and probably you know about this Schrödinger's cat paradox, which is more likely more related to the superposition principle, not just about this entangled pair, but they are also deeply connected. So let's look at what Einstein said. So in this paper, written in 1935, he actually discussed about these problems with his colleagues, including Podolsky and Rosen, which is why we call it EPL Paradox after their last names. And actually, they challenge the completeness of the quantum mechanics. So what they say is there are certain principles they already accept. For example, the measurements of the system always force the system jump into the right states. They probably accept this. And they also know that there is an uncertainty principle following the standard quantum mechanics. Then they actually imagine that something is not working as we expect in this proposal. So they think about the same Gedanken experiment. It's always same. We have a quantum machine in the middle, and we throw the two balls in opposite directions. And each ball may have a color, or in this language, it has the direction of this arrow, which is corresponding to the angular momentum, or the rotation directions. And this is the quantum states we have in the standard quantum mechanics. And Einstein said, first, the Alice measured this quantity, the direction of the arrow along the z-axis. So this is the first measurement. And he accepted. Then Bob can choose any direction to measure the same quantity. He doesn't need to measure this direction of the arrow or angular momentum along the z-axis. He can choose the same thing. So he can choose the same measurement along the x directions. And the standard quantum mechanics says whenever Bob does such kind of measurements, he must have the result either up or arrow with 50% probabilities. That's what the standard quantum mechanics says. And we came to the paradox because according to the uncertainty principle, it is impossible to determine this so-called spin or angular momentum along the x and z direction simultaneously. Remember, our object share the quantum states, and this is our original quantum state. After Alice and Bob's measurements, we know the Sx or Sz simultaneously, which is not allowed by the quantum mechanical principle or uncertainty principle. And Einstein said, oh, this is the paradox, and someone has to resolve this issue. And in his paper, he actually provided all the solution, which is surprising. So Einstein's view, obviously summarized by the point 1, he said, quantum mechanics may not be complete. He doesn't say it's wrong, but probably it's not complete to describe our world. And this is what the Einstein actually believed. And he tried to develop maybe different approaches. But in the same paper, those authors, including Einstein, they also provide different alternative possibilities. For example, he said that maybe those two quantities, the angular momentum along the x and z directions, they do not simultaneously exist in our reality. Then actually we don't need to think about this paradox. And that's certainly consistent with the other physicist view, including the Bohr. We call it sometimes the Copenhagen interpretations. And he also pointed out that we don't need to arrive at his conclusion if we accept this second point in his papers. Okay? So this is what actually Einstein and Podolsky and Rosen propose and point out in their papers. And there are still many other interpretations to resolve this kind of issues, including the many-word interpretations or Bohemian quantum mechanical interpretation. But the point is, until 1960s, all these arguments was regarded as the philosophical questions, simply because for the physicist, there is no way to double-check those kind of statements using some experiments. So it might be theory or philosophical questions. But of course, there are some gentlemen, like John Bell. He actually took a look, at this problem very carefully, and he actually formulates some framework to test out these possibilities. But in his view, he actually make the situation very clear that this Einstein's view can be captured by two concepts. First one is the local, and the other one is the realism. So as I said, the color of the ball may exist in the local frame. So the localism, it can be understood as there is no way to transmit the information of the measurement from here to there instantly. That's impossible. Okay? So the other important concept is the reality. So whatever you measure through your measurements, this measurement should be determined by the hidden information of your object. Seemingly, it totally makes sense in our life. But John Bell actually formulated some constraint that if this local hidden variable theory exists behind our quantum world, there must be some constraint we have to satisfy. So he considered the same Gedanken experiments, and he actually formulates some mathematical inequality that, and he concludes that any local realistic theory, the inequality he proposed has to be satisfied. So this is what this Bell's inequality said, and whenever somebody proved this, his inequality can be violated, which means this hidden variable theory is not the way we understand our nature. But unfortunately, he proposed these ideas, but no one could test his ideas because his original paper was written in a very abstract way, and because of some detection issue, it was very difficult to test his ideas. And our first gentleman, the John Clauser, and several other colleagues, they actually reinterpreted this Bell's inequality in their language. And this John Clauser is basically experimentalist. So he tried to basically rephrase this Bell's inequality into the real experiment. Sometimes we call this inequality as CHSH after the last name of the authors. And what they do is very interesting. So in our Gedanken experiment, we have Alice and Bob, and they assume that each person makes 2 measurements at every event. So we call it A1, A2, B1, B2. And through those measurements, this Alice and Bob take the value, either 1 or -1. So this SA1, SA2, and so on, those are the values they got through the measurements. This is very classical way. But according to this local hidden variable theory, this is always true because locally the measurement value exists in any event. So we always measure either 1 or -1. This is their setting. And what they do is, they consider this rather peculiar summation of the product of their measurements. And they conclude that we only have 16 cases because Alice measure either 1 or -1. We have 4 different variables, so we have 16 different cases, type all. And it turns out that the summation always gives us either 2 or -2. And this calculation totally makes sense according to this local hidden variable theory because every measurement value exists in any events on either Alice and Bob's side. And eventually, they conclude that if you have 100 events, 1,000 events, you measure the average value of this, the sum of these products. Well, because sometimes you get +2, sometimes -2, after averaging, the ensemble averaging, you end up having some value smaller than 2. And this is a very hand-waving argument, but mathematically he proved that this is always the case for any local hidden variable theory. And this is called the basically Bell's inequality or CHSH inequality. But still, this is the theory. So the Clauser actually called his friends at UC Berkeley because there was some machine which was not built by himself, but they actually modified. And he tried to confirm his inequality using some atoms. So this is the real apparatus they actually use. They basically generate 2 balls, which is actually photon. So they generate the one photon moving to the left, the other photon moving to the right. By using some atoms described in these schematics, they use some calcium atoms, and they somehow let them generate the 2 photons, and they confirm this inequality is violated, with a very high confidence. And this is the first experiment that showed the violation of the Bell's inequality or CHSH inequality in our history. But of course, their experiment was not perfect yet. First, the generation of those 2 photons is very inefficient. It's because of some experimental problem in their detections. Also, in his first experiment, he used very fixed directions. When he measured something, he never measured different directions. He only measured fixed directions. And people realized there might be a small loophole that although they show the violation of the inequality, who knows, maybe the hidden variable just works like that because we only have a very peculiar or certain configuration. Maybe this hidden variable theory already set the right value such a way that he observed the value in his experiment. So although there are some loopholes, he actually let the physics community open the eye to this quantum entanglement. And the second gentleman, the LNS Pan, he actually looked at the same problem in Paris, for instance, and they tried to improve the efficiency of their detection and generation of the 2 objects I mean, they use the same photons from the same calcium atoms. But most importantly, he tried to remove this very important loophole. In the first experiment, they actually fixed the angle of the detectors, but here he tried to make everything random. So in his experimental schematics, he actually used this rotational or some time-varying device to screw up this detection angle in a kind of random way. It was not completely random because of some technical difficulties in these days, but he tried to remove this loophole by modulating the directions. Another very important thing was the distance between Alice and Bob, because in the first and second experiment, the distance between two detectors was just 5 to 6 meters. And whenever you measure something on your left-hand side, who knows, maybe there might be a fairy that just talked to Bob, or I measured this on the Alice side. Who knows? So they carefully calculate how long it takes to travel from Alice to the Bob. It turns out to be tens of nanoseconds. And he just makes sure that he randomized these detectors faster than that time scale, which means even though the fairy tells what to measure to the Bob, it cannot explain their observations. So this is a very important step, that this quantum mechanics, he proved that quantum mechanics is correct. And our world behave following the quantum mechanics, not following the hidden variable theories. Well, we have another gentleman, Anton Zeilinger. And after those two experiments and a bit more experiments, actually the physicists in the physics community, they opened the eye to the importance of the entanglements. And this gentleman and his colleagues, quite many colleagues, they started to use this entangled pair or entanglements as a quantum resource. Because in these days, we are quite familiar with the technologies using the quantum something. For example, quantum computing, quantum teleportation, and so on and so forth. But for most of this technology, we need a quantum entanglements. And this is the gentleman who actually used it as a tool or resource. And for example, they demonstrate this quantum teleportation by entangle 3 objects, not 2 objects, for instance. So far, we discussed just 2 balls from this quantum machine. But if you bring another ball to the system, you can actually transport the quantum information from here to other city. This is one of his very important contribution. And in these schematics from the Nobel, the web page, they put this crystal instead of the atoms in the schematics. So he's one of the first guy who used the nonlinear crystal instead of the atoms to generate 2 photons or many photons. And this is a very important step towards the quantum technologies in these days. He did too many things, so I cannot list up, but quantum teleportation is one of them. He also explained how we swap the entanglements. So I have one entangled pair, I have another entangled pair. You can actually swap, make them interact. That's called the entanglement swap. This is the key concept to make the quantum repeater. And quantum repeater is more like the very important the components for making quantum internet in the futures. And another important contribution from this Anton Zeilinger is he actually demonstrates the entangled pair with 3 particles, for instance, or 4 particles, or many particles. After they demonstrate this entanglement of many particles, people realize that, oh, then we don't need a Bell's inequality. If you demonstrate this entanglement of many particles, it immediately says that this hidden variable theory doesn't work. So that's another important contributions. And excuse me. Excuse me. And those three gentlemen actually make us to realize the importance of this entanglement for the foundation of quantum mechanics, but also for this quantum information science. And probably you know that this entanglement quantum states is a key for realizing this quantum information science. One example is when you have a quantum information in your system, you need to actually store and transfer and processing this quantum information. To make that happen, we usually need a quantum entanglement. For example, when you transport the quantum information from one city to the other city, Zeilinger and other colleagues, including Gyuboong Pan in China, they actually realized this quantum teleportation using the satellites, and this is one of the application of these quantum entanglements. And obviously, quantum computing, we need entanglements to process this quantum information in these days. And this is the last slide. And this quantum technologies has been well recognized in different countries and continents. And this is one of the example how this EU plan out for this quantum information science. They actually identified 4 different pillars, including quantum communications and quantum simulations, or quantum sensors and quantum computers. We don't need to specify what it is exactly, because this quantum science is pretty much very entangled between these 2 pillars. But what's important behind this development is basically the entanglements. Because we know the entanglement is there, is real, and we can actually use it as a quantum research. And I came to the last slides. I congratulate to all of our colleagues here, and thank you for your attention. Okay, so I invite any questions from audience or the Zoom.
Thank you for the talk. So I have a question about, can you explain the many particle entanglement, and does it violate the monogamy of entanglement property?
So, okay, so what was your last comment?
So the many particle entanglement, so does that violate the monogamy of entanglement? Like only 2 particles can be entangled. How does the third particle enter into this?
Oh, well, yeah, the question is how do we describe the many particle entanglements? Well, there are many different configurations, but one thing you can, well, in our previous entanglement states, entangled states, we put spin up, spin down plus spin down. Oops. Okay, here. So this is the 2 particle entangled states. But there are different kinds of entangled states, such as you can imagine spin up, and spin down, for instance. For the many particle case, the easiest way you understand is what if you have 3 particles, you can imagine up, plus down, down. That's one of the examples, simplest case. If you have n particles, you have n spin up and n spin down. But this is only one of the examples. There are many different configurations you can imagine.
I think regarding monogamy of entanglement, as far as I know, the statement is if shareability of entanglement between party and A and B is maximum, then they cannot entangle with third particle C. So let's say in GHZ states and I think WSS maybe. So shareability of the entanglement is also maximum, but in the GHZ state, if you write the reduced density matrix of the states A, B, or AC and or BC, so they are actually identical. So also the shareability of entanglement is also maximum, but they behave identically. So I think to answer to your question is, I think if shareability of entanglements is not maximum, then they can entangle with third particle C.
Yeah, actually, your picture is correct. So if you have three particles, we have to first consider how these two you can choose two. You have to think about how they are entangled. Depending on the magnitude of the entanglements, we have a different scenarios. So, but if you go to the n particle limits, then it's more complicated, but still the same approach can be achieved.
Thank you for the wonderful talk. I have a very simple question related to the quantum repeater. I'm wondering, how do we build the quantum repeater by entanglement? What is the technique involved?
Yeah, so it's a great question. So the question is, how do we build up this quantum repeater or quantum network? So basically, if you imagine our internet in our current technologies, what we do is we need to send some signal, usually optical lights through the fiber. So the same principle will be applied to the quantum network or quantum internet. The question is, whenever you generate some quantum information, for instance, because we need to transfer the quantum informations. Usually whenever we do the quantum teleportation, we generate the quantum entangled pair of photons, and one of the photons goes to the other CT through the optical fiber. The question is, the fiber always have a loss. So it cannot propagate more than, for example, several tens of kilometers. So whenever we lose the photons in the fiber, we also lose the quantumness or entanglements or purity of these quantum states. So before we destroy this quantum information, we need to put some device in between and make a copy of my original quantum information. So that's why the quantum repeater should be there. For example, every 10 kilometers, I need to repeat my quantum information. And if you have a 10 repeater, probably you can achieve 100 kilometer communication using these quantum informations. So the technique we use is, it's called entanglement swapping. So I have some quantum information encoded in my quantum states, but I need to use these quantum entanglements to transport. So at the quantum repeater, I have one entangled quantum states coming from the CTA, some city, and at the quantum repeater, I generate another entangled pair, and I make them interact. And through this entanglement swapping, basically you can repeat this quantum information from here to there, for instance. So this quantum repeater is basically amplifier with correct quantum information that I want to transfer. So this is the key component of the quantum network in the future. It was demonstrated in the laboratory level, but the real commercialization is still in questions.
Stuart Friedman was the co-author with Clauser on the first paper in 1969. Mm-hmm. As you probably know, Stuart died in 2012. If he were alive today, so I know a little bit about the history. So he was a postdoc with Clauser at Berkeley at the time, and it was actually Stuart who proposed. He
was a student, right? The Friedman was students.
Friedman was a student of Eugene Cummins. And I think Stuart proposed this experiment and then dragged Clauser along. So Stuart surely would have shared the Nobel Prize if he were living. So who do you think they would have eliminated, since they can't have more than 3?
Well, that's very challenging questions. But if Friedman is alive, then very likely the Anton Zeilinger will be the next maybe Nobel Prize winner in the future. Just because if you look at the history, as we discussed it, it's very important to make a strong statement that this Bell's inequality could be violated in a quantum mechanical way. And this Clauser and probably Friedman and this LNS Pan, their contribution is significant. So I don't think no one among those three can be eliminated. But on the other hand, Anton Zeilinger demonstrated so many things as an application of these quantum entanglements. So maybe at this time, yeah, maybe he will be eliminated from this Nobel Prize this year.
Okay, if there are no further questions, please join me in thanking Gyuboong for an excellent lecture.
Thank you.